Hello class, welcome to section 14.2. We're focusing on complements and of course the union of events. So let's just jump right in. Best way I can explain complement is with these examples. For example, if the chance of rain tomorrow is 40%, what is the probability that it doesn't rain tomorrow? Obviously it's going to be 60%, because 60 plus 40 gives us 100%. This is the idea of a complement. If I roll a single die, the probability of rolling a 2, when 2 pops up, is 1 out of 6. So what's the probability of not rolling a 2? And again, it's going to be 5 out of 6. Again, this is the idea of a complement. A complement of an event is a probability such that they add up to a full probability of 1, or 100%. Or more effectively defined here, the set of outcomes in a sample space not in the event. So generally PE is used to represent the probability of an event. So I can say P of not E, as written here, is the probability of an event not happening, of course. Also written as PE prime. So two ways of referring to the complement. And sometimes it's also written, and I can't do it with my with PowerPoint, but I might be able to illustrate it with the marker here. Another way of writing it is with a line over top of the event itself. So right here. I don't know if that's clear now. Let me make it a different color. So if I put a dash over top of the E, and I'll try my best there. That's another way of representing a complement. So again, the probability of E and then the probability of the complement is going to add up to 1. So for example, if the probability of event is 2 out of 13, then the probability of the complement is 11 out of 13. And this brings us to the concept of mutually exclusives. Now when we get into probability of union, and probability of events, we want to consider the idea of mutually exclusive. What that means is two events can't occur simultaneously. For example, getting heads and tails at the same time. And this is an event that's, or two events that are considered mutually exclusive. Again, it just can't happen at the same time. So we say if two events are mutually exclusive, then the probability of the union is the sum of the probabilities. So basically, again, the point of this section is to know how to do the sum of probabilities of a union. And we get there by identifying if two events are mutually exclusive or not, or multiple events, I should say. And if they're not mutually exclusive, in other words, if there is some element of overlap, they have some elements in common, or for those of you familiar with the union and intersection, if two events have an intersection of some sort, then we have to subtract those common elements. Otherwise, they're counted twice. So let's look at some examples. The probability of mutually exclusive events, or probabilities of union. If A and B are mutually exclusive, then P of A or B. And again, the or is important. The phrase or in probability signifies union, as opposed to and, which signifies intersection. So we're talking about probability of unions, so we're looking at A or B. Is one way it could be written. So we say if A and B are mutually exclusive, in other words, again, there's no common ground. Like flipping a coin and rolling a die. When I flip a coin and roll a die, there's no common event there. There's no heads or tails on a die. There's no 1 through 6 faces on a coin. So hence they're mutually exclusive. In which case, when you find the probability of union, you just add the individual probabilities. So the probability of A or B is equal to the probability of A plus the probability of B. But if I do not have, and again here's an example, rolling a 4 or a 6, there's no overlap, so I add my two probabilities, the probability of 4 plus the probability of 6, which is 1/6 plus 1/6, or 2/6. And again, like I said, you can reduce that to 1/3 if you would like. Now, if they're not mutually exclusive, then as I said, we have to consider the fact that certain events are, certain elements are being counted twice. So for example, P of A or B equals the probability of A plus the probability of B minus the probability of A and B. So that means minus their intersection. For example, the probability of drawing a 10 or a black card from a deck of cards. So this is equal to the probability of drawing a 10 plus the probability of drawing a black card minus the probability that you draw a 10 and a black card, or a card which is both. So again, the probability of drawing a 10 is 4 out of 52. There are 4 10s in a deck. The probability of drawing a black card in a deck of 52 cards is 26 out of 52. Half the deck is black, half the deck is red. How many cards are both a black card and a 10 card? Now, there's 2 of them in a deck. So that's considered the intersection. Which cards are 10 and black? So then to find the probability, we add the 2 individual probabilities, 4 out of 52 plus 26 out of 52, and then subtract the common element, which is 22 out of 52. Which gives me 28 out of 52, or if you want to reduce, it gives me 7 out of 13. Another example. Paired dice are rolled. What is the probability that the total showing is either odd or less than or equal to 8? So we're considering 2 possibilities here. The fact that we roll a pair of dice and the sum is odd, an odd number, or that sum is less than or equal to 8. And I provided a little graphic that should help us lay out what our possibilities are. So if we're rolling 2 dice, we have a sample size of 36, as you can see. And these are the different possibilities of adding these numbers. And you notice that in this particular case, for example, 3 and 1 and 1 and 3 are counted as separate rolls. So order isn't critical with these. We count each one individually. So my first probability is, what's the probability that I have an odd number from these sums between 2 and 12? And again, I say between 2 and 12 because, looking at our chart, if we're adding each of these rolls, what I get, the lowest number I could possibly get would be a 2, because I've rolled 1 and a 1. So then, probability that's odd means that I'm choosing numbers between 2 and 12, which are odd, and there are 18 possibilities if you go through and count. Or obviously half. So now it's the probability of a sum less than or equal to 8. Now if you look back at our graph, one way of course you can do this is to count them up. What are the total number of sums less than or equal to 8? But if you want to speed through it a little bit, we can use our complement rules and say that, well, the complement of the sums that are less than or equal to 8 is the sums that are greater than 8. That makes up the complement. That's everything that's not in the original event. So again, this is one option. To speed this along, you can find out instead what's the sum, how many sums greater than 8 are there, and then take the complement of that to find what we want. So for example, in this case, the probability that we have a sum that's greater than 8 is 10 out of 36. There are 10 sums in this chart that are greater than 8, which means the complement would be 26 out of 36. So now, to find our overall union, the probability of union, the probability of an odd number or less than or equal to 8 is equal to the sum of the probability of getting an odd sum plus the probability of a sum less than or equal to 8 minus their intersection, the probability of an odd number that is also less than 8. That comes out to be this. 18 out of 36 plus 26 out of 36, that's the sum of the first two parts, an odd, and then a sum less than or equal to 8. And here again is a perfect example of why you take away the intersection, because they're counted more than once. If I were to stop here, my numerator would be bigger than my denominator. I'd have a percentage over 100%, which of course we can't have. So there are 12 sums that are less than 8 and also odd, so I subtract that for a probability of 32 out of 36. And that would be my answer. So a couple of standard examples of some ones you can see. And the book had a good example in it, which I'm going to repeat here and just explain how they went about it. I thought that, because one thing I thought is the way it flowed, the way they explained it was a little jumbled. I thought they could have streamlined it a bit. So example 4 on page 667. Survey of consumers comparing the amount of time they spend shopping on the internet per month with their annual incomes is produced below. If we select the consumer randomly, what is the probability that the consumer neither shops on the internet 10 or more hours per month, nor has an income of above $60,000? So I reproduced the chart, and here it is. So we're trying to find, again, what's the probability that the consumer neither shops on the internet 10 or more hours, nor has an annual income above $60,000. So there's two parameters we're considering. Now for simplicity, let's find the complement. Similar to what I did in the previous example, finding the complement sometimes makes things easier for us. We have to do less work. So the complement of neither nor would be either or. It's neither this nor that. The complement is this or that. Is one way of thinking of it. Or here's the graph from the book. If you look at it in terms of a Venn diagram, if T represents the time people who spend more than 10 hours per month shopping on the internet, and A represents incomes above 60,000, neither nor would be everything that's not inside the union here, inside the intersection. So as you can see, both 10 plus hours shopping above 60,000. So the combination of both shopping more than 10 hours, income above 60,000, is in the middle here. It's the intersection of the two Venn diagrams. So the opposite of that, the complement, is everything outside of it, which you can see outside of these circles is neither 10 plus hours shopping nor income above 60,000. So if we want to find the probability of T union A, as you can see here, and then its complement. And you can see in figure 14.1, and before I go, let me just go over this one more time, just to make sure that there's no confusion with this graph. Again, what we're asking for is neither 10 plus hours shopping nor income above 60,000. So if you look at it in terms of, again, the Venn diagram, the opposite of that, the complement, is that we do shop more than 10 hours and we have income above 60,000, which is the intersection of these two sets. So again, the complement is everything that's not in there. Now you might think, well, wouldn't that include parts of those circles themselves, not just this kind of lightly shaded area around it? And I'd say no, because, for example, we wouldn't include this outer blue area. And let me highlight this. We wouldn't include this area out here, because everyone in there does spend 10 hours or more shopping on the internet. We don't want that. For the same reason, we wouldn't include everything inside this circle, because even in that sliver, in this particular section I'm partitioning off, everyone in there has an income above 60,000. So that's why we're avoiding not only the middle of these two intersections, of these two Venn diagrams, but each individual Venn diagram itself. We're only interested in the universal part outside of it, if you remember back from your chapter 2. So again, the idea is if we find the probability of the union, T union A, and the complement is what we want. So the probability of T union A is, again, the probability of the 10 hours or more, plus the probability of the income above 60,000, subtracted minus their intersection. And that gives me, let's see, let me bring this down so you can compare better. There we go. So the probability of T is 480 over 1600. Probability of A is 496 over 1600, and their intersection is 192 over 1600. And when I subtract, I get 784 over 1600. Now that's the probability of their complement. So we want of the opposite of what we want. So we want the complement. So we'll say 1 minus that gives us 816 over 1600. Or another way of thinking of it is 784 over 1600 is 0.49 as a decimal. So you think, well, what would I add to that to get 1? That's where I get the 0.51. And again, I'm getting those numbers from up here. 496 came from this total. 480 came from this total. Now 192 is, of course, the time in between. Now keep in mind, you could have done it the other way. You could have said, well, just looking at this chart, what areas are outside of this definition? What areas are not 10 plus hours? What areas are not above $60,000 income? So everything that's not 10 plus hours, of course, is these right here. Everything that's not above 60,000 is all these right here. Then we want both. We want neither above 60,000. So we're starting with considering all these possibilities, or really I should say these. In addition to that, we don't want anything 10 plus hours, so we gotta get rid of those. So we're focusing on these right in here. Now this again. So again, here we are. Just based off definition, looking at my chart, I focus on these four numbers. So since the grand total is at 1600, let's see what this gives us. That means I'm going to add 208 plus 144 plus 192 plus 272 gives me 816. That should look familiar. When I divide by 1600, I get the percentage that I was looking for, which was 0.51. So you see there's another way of doing it. We can use a complement to speed things up, or we can just do it in a very straightforward manner. Either way, obviously gets us to the result that we want. You may prefer doing complement to shorten things up. If you prefer to be a little more direct and just say, well, just going off definition, I can just figure out what those are, that's fine too. It's whatever makes the most sense to you. So that concludes section 14.2. As always, if you have any questions, feel free to contact me, and have a good day.